Recording in progress.
Hi students. In this lecture, I am going to discuss a work energy theorem. Let us see what is the statement of work energy theorem. The net work done or work done by net force on a particle is equal to the change in its kinetic energy. I am repeating, the net work done or work done by net force on a particle is equal to the change in its kinetic energy. Let us see what is it and how to get it. Let us consider a block of mass m which is placed on a smooth surface and a horizontal. So we are taking a block of mass m which is placed on a smooth horizontal surface, or we can take rough also, or let us take rough surface. Apply force F and assume block is moving. See number of forces acting on the block. Applied force, gravitational force, normal reaction, and frictional force. If you are taking rough surface, frictional force. So when block is moving, now we can calculate work done by applied force, by frictional force, by normal reaction, and by gravity. So calculating work done by each force and taking the algebraic sum, that is giving us net work done. That is giving us net work done. So it is by applied force, by frictional force, by normal reaction, by gravity. And taking it is algebraic sum of all this. Algebraic sum means if it is a positive, taking positive value. In this we can see if block moves by applied force, work done is positive. By friction, it will be negative. So taking positive value, taking a negative value. By normal reaction, no work is done. By gravity, no work is done. So like this, taking the algebraic sum. So sum of all this gives us net work done. This is one way of calculating net work done. The other way is first calculate net force. So here you can see normal reaction balancing mg. So both are cancelled. Remaining is F minus F. That is net force. So calculate work done by net force. Okay. So net work means either sum of all work done, otherwise work done by net force, and that is equal to delta K. Okay. Let us see how to get it. So work done by net force I am taking here. That is equal to integral F bar dot ds bar. This is now net force. F bar net dot ds bar. Okay. Right. Let us assume between these two vectors angle is 0. Then see what we can write here. In the place of net, mass into acceleration. In the place of acceleration, I am writing v dv by ds. Okay. Into ds. Now this becomes, take m outside, integration of v dv. Okay. Let us take initial velocity v1, final velocity v2. Now this becomes v dv becomes v square by 2. That means it is equal to half m v2 square minus v1 square. So net work done is equal to the change in its kinetic energy. Okay. This is statement of work energy theorem, right? Let us see now problems basing on this to get more clarity. Means how to apply that. See what is the question given. A body of mass 1 kg is a drop from a height of 10 meter. Its velocity just before touching the ground is 12 meter per second. Calculate the work done by air resistance during the fall. During the fall. So take Z, means take G value 9.8 meter per second square. So we have to calculate work done by air resistance. See, we are knowing that when block is moving down, its speed keep on increases. When speed keep on increasing, this resistive force also keep on changes. So here the advantage of work energy theorem is we can calculate work done by the forces which are not known to us. We can calculate work done by the forces which are not known to us. See how we solve it. Given mass 1 kg, dropping from a height of 10 meter, just before touching ground, its velocity 12 meter per second and G value 9.8. Okay. So if you want to use work energy theorem, that is net work equal to delta K. In this, body is a drop, means initially velocity is 0. Just before touching ground, velocity 12 meter per second. Okay. That means now in this delta K value is known. What else left here? See carefully. One is gravitational force, which is downwards. Other one is air resistance. So work done by air resistance. Sum of these two must be equal to delta K. So only two forces are acting. One is gravitational force, other one air resistance. So only two forces are acting. So work done by these two forces, sum of these two should be equal to delta K. And you can see by gravity, gravitational force is downwards and displacement also downwards. Therefore, F into F is now mg. Mg is now 9.8. So m is 1, g well 9.8. mg displacement equal to 10, right? That is work done by gravitational force plus work done by air resistance, which we have to calculate. That is equal to delta K and delta K value. Finally, see what happened. Just before touching given 12, that means half m v square 12 square 144 minus initial value. Therefore, by E resistance work done is equal to, this is how much? 72 minus 98. Okay. This is now work done by air resistance. Okay. How much it is? This is a 20 and this is now 26. So it is now minus 26 joule. That means because of air resistance, work done is negative. That means its energy has decreased. Okay. So like this, we can calculate work done by unknown forces. Right. Let us see the next problem. A block of mass m is connected to one end of a massless spring whose other end is attached to the ceiling. Now the block is released from rest suddenly and the spring is in its natural state. That means at the time of releasing, spring was in its natural state. Means no compression, no elongation. Find the maximum elongation of the spring. Okay, right. See how we start the problem. First, let us draw a diagram for this. Attaching now, you see the spring. To the other end, a block of mass m is attached. Okay, given that at the time of releasing, spring was in its natural state, right? Now we have to calculate maximum elongation. If you observe carefully, as long as block is moving down, elongation keep on increases, right? Once a block comes to rest temporarily, once the block comes to rest temporarily, elongation becomes maximum. And after that, block moves upwards. Okay. So when block comes to rest temporarily, that means after that block starts moving upwards. Okay. That becomes maximum elongation. So when velocity becomes zero once again, so initially velocity is zero, finally also velocity is zero. So delta K how much? Zero. And see on the block how many forces acting. One is gravitational force, second spring force, right? And spring force is now variable force, right? So first calculate work done. I can write here delta K equal to work done by spring force plus work done by gravitational force. By gravitational force work done directly, force is a constant, so mg. If it is moving down by a distance x, if it moves by a distance x, then displacement is x downwards, gravitational force also downwards. Therefore, by gravity, work done is a positive. Okay, right. Now focus work done by spring force. Since spring force variable, we have to use integration. So integral f value, if elongation is x, spring force kx, displacement, take a small displacement dx, f into ds into cos of the angle, cos 180. Students see carefully, block is moving down, so displacement is downwards, but spring force is upwards. That's why I have taken here 180. Okay. Now this is equal to cos 180, take minus 1 minus outside, remaining k constant outside, spring constant, x dx, x square by 2. That means by spring work done is negative. Okay. Sum of these two equal to 0. Right. Now substitute this value in this one and by gravity in this one. Then see what we get. We are going to get mgx is equal to half kx square. Right. So I have taken these two values in this equation. Okay. Then we are going to get mgx equal to half kx square. So from this, see what we get x value. X equal to 2mg by k. That is maximum elongation. So like this, we can use work energy theorem to calculate maximum elongation. Okay. And this question was given once in previous IIT. Okay, let us move on to the next problem. So this question already we have solved it in the previous lecture. So same question, same values. 2 kg block placed on 3 kg block, applying force at 10. Calculate work done by friction on upper block in the time interval. 0 to 3 seconds. Okay. Given coefficient of a static friction 0.3 and that of a kinetic friction 0. So I want to solve the same question now by using work energy theorem. Okay. That's why taking same question. See once. So 3 kg block on that 2 kg block. Applying force on 3 kg block horizontally. Given mu s 0.3, mu k value 0.2. We have to calculate work done by frictional force on 2 kg block, right? So earlier what we have done, we made calculation for frictional force, right? Between 2 kg and 3 kg block frictional force. Next, we made calculation for displacement, right? So we got acceleration A equal to 10 by 5, 2 meter per second square, right? Then we got displacement equal to half A t square displacement, and we got frictional force F equal to 4 Newton, right? Because acceleration 2 means on this net force is nothing but frictional force, okay? Therefore, frictional force is a 2 into 2, that is a 4. So by taking this, we got by friction work done is 4 into 9, 36 joule. Okay. Now what I am saying is we can solve same problem by using work energy theorem. That is, see carefully, on 2 kg block, how many forces acting? One is frictional force, mg downwards, normal reaction upwards. These two are balanced. Frictional force is now net force. What is it? Frictional force is now net force. Then by frictional force, work is nothing but net work done. And this net equal to delta K. Initially, block was at rest. Okay. So if I can find its velocity, I can calculate its kinetic energy. So what I'm doing here, acceleration 2, time given 3 seconds. Therefore, velocity equal to acceleration 2, time is given 3. So V equal to A into T, that is now 6. 6 meter per second. Since we got velocity finally, initial was 0. So delta K equal to half m v square minus 0. Okay. That is equal to 6 square, that is 36. So we can solve like this also by using work energy theorem. Okay. So question same, but there we have taken like what is the frictional force. So in this, we did not make any calculation for frictional force. Getting the point. Just we made calculation for velocity and we got the answer. So this is another way of solving the problem. Okay. Right. Let us see the next problem. Right. This question is taken from Irido. See once. A locomotive of mass m starts moving so that its velocity varies according to the law V equal to A root S, where A is a constant and S is the distance covered. Find the total work performed by all the forces which are acting on the locomotive during the first t seconds after the beginning of motion. So given velocity v equal to a root x. In first t seconds, we have to calculate work done, right? Net work done. Right. So we are going to use now work energy theorem to calculate this. Right. First of all, write down the given data. V equal to A root S. Right. So we have to calculate now net work done. Right. Net work done is equal to delta K. Initially it was at rest. Now if we know distance covered, we come to know what is velocity. Then we can calculate what is delta K, right? So for that, see what we can do here. So to find acceleration means to find velocity, sorry, to find displacement, we require now acceleration because displacement is equal to half into, let us take acceleration is A dash, half A dash T square. So we require acceleration, right? Since given velocity as a function of distance traveled, we can write acceleration equal to A dash equal to V dV by ds. Okay. V value A root S. Next dV by ds. dV by ds. A into 1 by 2 root S. Right. That is root S gets cancelled. It is now A square by 2. That is now acceleration. That means it has a constant acceleration because A is a constant. Now I can find here displacement at S equal to E half A dash T square. That means now what is velocity? Or I'm writing directly here delta K equal to half M V square. That is equal to half M in the place of V square. In the place of V square, what I have to write? V square means it is A square V square into S, right? In the place of S, what we have to write? Half A dash. A dash is A square by 2. Half A dash T square. See carefully once. Half M V square. V square is A square into S. So A square. In the place of S, half A dash T square, right? Then see what we get here. Half. It is 1 by 8. 1 by 8 M A square A power 4 T square. This is now net work done, or it is a total work done, right? So like this, we can use work energy theorem to find net work done. In this, what happened is we are given velocity as a function of distance traveled. So we are thinking like if we know S value, then we come to know V value, then we can calculate delta K. That is our key point to start the problem, right? So final answer is 1 by 8 M A power 4 T square. Okay.